Okay, so a few programming notes to begin with. You guys did not have class last Monday because of the holiday break, but it's still expected that you are responsible for the lecture material that we went over on Wednesday. Okay, so those notes, that lecture, and the the drive notes that I have are all listed as lecture 4 on Canvas. Today we're going to be doing lecture 5, and so there's no class on Wednesday. Okay, now that doesn't affect you guys, but I'm telling these guys that they're responsible for this week's material through this lecture. Okay, and I apologize that we won't have class on Wednesday, but I have faculty obligations, so it's not my fault. I wish we were having class on Wednesday instead, but we're not. So this is the one lecture that covered this material this week. Next week we'll get back onto our normal schedule of having 2 lectures per week. The other thing, so this material covers chapter 3.1 through 3.2. You guys can't see a thing. It covers chapter 3.1 through 3.2 in your Zybook. And so you're going to want to make sure that you've read that material, and that is your reading assessment assignment for this week. We're going to be talking about scheduling. We're going to begin our discussion on the chapter on scheduling. Having talked about processes and threads and talked about some of those details, it's now time to talk about sort of the other part of that is, if we're going to have multiple processes, then how are we going to decide what process does what thing at what time? Okay, and that's going to be dealt with by the scheduler. We are not quite done with processes in terms of the exercises that you have. So you'll recall that exercise 2 had you get some basic understanding with the C programming language and compiling C programs on the CS server. Continuing from that is exercise 3. Where we left off with exercise 2, we had a program that could read commands from standard input, multi-word commands from standard input, and give them back to us. And it was designed in such a way that we didn't have to necessarily limit the size and characters of the commands that could be read in from the user. That was only the first of 3 parts, the 3 main components for any shell program. The second part of that program, and the third part of that program are covered in exercise number 3. So the first part of exercise number 3 is to do the parsing, okay? And for us, we're going to make it easy. Parsing our commands is basically the same thing as tokenizing our commands. Now, when I say that, does that mean anything to you? Tokenize? Basically, it means take each individual word, okay, and treat them separately, right? So for our shell, all commands have to begin with the name of a program, okay, like ls or echo or vim, okay, space, some parameter, space, some parameter, space, some parameter. And you're going to have between 0 and n parameters, but they're all delineated by a single space, okay? No special characters like backslashes or quotation marks, okay, are going to be allowed. So that's actually going to simplify our process for us. I'm not going to go over all the detail here. This part is, in my estimation, the hardest of the 2 parts. Unfortunately, you really need to do this first, or maybe fortunately, right? Because then you'll be motivated to go ahead and get started on it and ask me questions about it. But effectively, what the parse section does is it returns an array of pointers to character pointers, okay? So in other words, a string, right, is an array of characters, and it can be referenced by a character pointer, right? And what this function is going to do is it's going to break that into individual character arrays, right, each of which is pointed to by a character pointer, and store that in a dynamically allocated array of character pointers, which is pointed to by a character pointer pointer. Okay? So if you don't remember that from 155/255, when you first started talking about pointers, you may want to go back and refresh your memory, like what's a pointer to a pointer? What does that mean? Okay? Because effectively what we're doing is we're returning an array of C-style arrays. Okay? So there's more detail about that. Hopefully this will help you out reading that. I've given you a reference to a standard function, string toke, and you want to make sure you're familiar with what string toke does. It's not straightforward, so make sure you are familiar with that. Well, it's a little bit straightforward, but there are a couple of wrinkles in there. Then once you have your array of character arrays, okay, character strings, C-style strings, then we have the execute command. And since we're on Linux, remember, and this is where processes come in again, remember the only way to start a new process is to run the fork command, okay? And the fork command works this way. When it's called, it creates a duplicate process that's completely the same instructions, same state as the parent process, and it returns a 0 to the child process and a PID to the parent, so some non-zero integer value to the parent, okay? So if the value returned by fork is 0 for you, you know you're the child, okay? Which means that you need to overwrite yourself with whatever it is that you're supposed to be. And the function that does that is execvp, okay? Exec function overwrites, changes the instructions for one program to become another, right? And VP stands for vector and path, okay? And there's more detail about that. The vector is the array of character arrays, and the path is just the name of the program, okay? I have given you a mostly complete function called execute. There's a couple of things in here. Basically, you just drop this whole thing into your code, but there's a couple of question marks here that need to be filled in by you. Okay? Hopefully that's not too difficult once you've spent some time looking at things. Okay? All right, so at that point, your screen, your shell should work like this. Tiny. Very, very terribly. Ah, there we go. Okay, so once it loads the HD version, it's easier to see. This is a screen share of me running the solution that I built for this exercise. Okay? So you should have a program that works like this, okay, when you're done. I wanted that hidden. Yes. So this is due, and then we're going to add the exit command as well to our shell so that we don't have to hit Control-C to stop the shell program running anymore. This is due a week from today, before midnight. So you should, yes. Yeah, a week and a few days. Yeah. So not Monday, but Wednesday of next week. Yeah. Okay. So if you have any questions about this as you're looking at it, let me know. You're better off getting started sooner than later. And certainly don't wait till the last minute because there are some things you're going to have to work out. Okay. Any questions? All right. Okay, so let's talk about today's topic, which is the scheduler. All right, now the scheduler has come up over and over again when we've been talking about processes. I probably don't need to draw this for you, but I will anyway. Recall the state diagram, the finite state machine, for all the possible states that every process can be in. Every process wants to be running. That means that it has its instructions being executed on the processor. How many processes can be consecutively running on the processor? Just one, okay? Only one can be there, right? So we've got hundreds, thousands, hundreds of thousands of other processes, and they are split between being ready to be put on the processor, to be executed, in other words, and being blocked, okay? Because they're waiting on some resource. So I don't know if you have taken the chance to look at last Thursday's lecture yet, but that was resources and resource management was one of the things that we talked about in that lecture, one of the things that you're responsible for. Yeah, so we learned that each resource has its own wait list associated with it. And so the aggregate of all those wait lists, right, all together, makes the overall system wait list. Okay, so this might be for resource 1, resource 2, resource 3, et cetera, et cetera, et cetera. Okay? So if you are running and you need a resource that isn't available, you go on that resource's wait list and you go into the blocked state. Okay? If that has happened, then another process needs to be moved from the ready state to the running state. Okay? It's also possible that you can go from blocked to ready because your resource is released. And it's also possible that you might be running and just be moved to the ready state. Okay? So we mentioned really 4 distinct times when we need the scheduler. Okay. Off of this, you'll see that we need the scheduler every time that a resource is not ready. We need the scheduler every time a resource becomes ready. Okay, so we need it here and we need it here. Now it's obvious why we need it there, okay? Because something came off of the running, off of the processor, and was blocked, okay? So we need the scheduler to decide which of these ready programs, and there's a single list, which is abbreviated RL, that's the ready list, okay? That's a link, or it's an array or a link or a data structure of process control blocks or links to process control blocks, okay, of all the processes that are ready to go into running. So we need to choose from this, okay? How do we choose from this? Well, that's some of the stuff we're going to talk about today. But in some fashion, we need to choose from that because a resource was not ready. We moved into block, and we needed to load another one onto running, okay? Perhaps less obvious is why we need this one to trigger a scheduling event, okay? We trigger a scheduling event here because a blocked process becomes ready, moves to ready, right? We need to determine, or we need to have the scheduler determine, hey, was that an important thing, okay? Did that need to go? Okay? Did that need to run? Was that, say, more important than the thing that's currently running? Okay? And if it is, then we'll do this swap right here where we take the running thing and move it to ready, and we move something from the ready list onto running. Okay? Does that make sense? So that's 1 and 2. A third time and a fourth time are not directly, they're not directly visible here. But one of the things that has to happen is that a function, or rather a process, has to arrive. Okay? So when a process begins, now there's something new to fight to be priority on this ready list. Okay? Because processes always arrive at the ready state. Okay? So when a process begins, the scheduler runs to determine if we need to do this swap again, given the new processes here. Okay? And when a process ends, right, then we need to determine, because what could have ended, right? Either the running process killed a child, or the running process terminated. It was done. Okay? So obviously, this is going to trigger, right, the scheduler, because the thing that was running is now done and needs to be, its program control block needs to be released entirely, not to mention just moved off of the processor. But this can also cause a reevaluation most of the time, because again, there's a new status in the ready list, okay, in terms of who needs to go next. Okay? And I said that there were 4 times, and that's true, but really there's a 5th time just overall, right? And this is just the OS, I'll call it the OS context switch. All of those changes, this is technically the context switch, right? Where you move one thing off of running and you move another thing onto. Anytime you move anything off of running and another thing onto, that's called the context switch. But sometimes the operating system, in order to, and in particular the scheduler, in order to keep things fair, if you want to call it that, or balanced, if you want to call it that, or there's some metric that we're trying to achieve, which is evaluated every once in a while, and occasionally it causes this to happen. It causes the context switch to happen. Okay? And I'm going to get into some details about how that might take place. Okay, so I kind of lied. There are 4 that are directly associated with this, and then there's a 5th one that is just the priority of the operating system. Okay. All right. Any questions about what I've said so far? Okay. Any questions? All right. So let's look at preemptive and non-preemptive scheduling. Okay. Scheduling algorithms fall into those 2 categories. Right? Non-preemptive scheduling is where you don't interrupt a running program period. Okay? You Don't interrupt a running program. So in other words, the process will continue until it either terminates or it blocks on a resource. Okay? So we are disallowing this context switch, okay, right here, right, on non-preemptive scheduling. All right, so if we don't allow this, what are the implications? Okay, who's talking? Okay, yes. Yes, I would agree with that. So it harms the illusion of multi-programming. Now, does it eliminate multi-programming? In the sense that we can still have multiple processes in the system, right, at the same time, competing for limited resources, all being recognized by the operating system as being available to run or waiting on some resource, then no, this still allows multi-programming, okay? So how might it harm the illusion of multi-programming? Under what circumstances?
A long-running process.
Okay, so you've got a long-running process, and I mean long-running at human scales, okay? Then it may seem like the computer is not doing anything to the user, right? Or at best is only doing one thing to the user, okay? So given that, sort of the opposite question is, when might you be okay with non-preemptive scheduling? Yeah.
When you have a computer that's trying to do one specific task.
Okay. Can you think of such a computer? Okay, I'd agree with that. Yeah. Large-scale industry application computers. If we don't have users that want multiple programs competing for resources at the same time, right? Then any computer with non-preemptive scheduling will be fine. If we have only small things to do, okay? If we have only small processes running, non-preemptive scheduling could be perfectly fine, okay? Because it doesn't take long on the human scale for any given program to finish. And in fact, it seems somewhat more fair, right? Because the first program to get there gets the attention first, okay? Unless it blocks on something, in which case the next program goes, right? And one way to schedule that is to do a first arrival scheduling. And we'll talk about some scheduling algorithms in just a minute. But to do a first to arrive scheduling gives us sort of a fair sense, okay? So great, from the user perspective, there are limited times where we might want to do non-preemptive scheduling like this. Now, from the processor perspective, is preemptive scheduling good?
Doesn't spend time switching between tasks.
What does that mean for us?
Gets more done.
Okay, gets more done in the sense that the processor usage time is maximized. Okay? Because there's a tension between context switching, which doesn't allow the processor to perform any meaningful process, okay? And maximum time, maximum usage. So in other words, the more context switching you have, the more overhead that's required, the less time that you're using the processor to actually do the processing that you want the computer to do. Okay? So if there is a batch system. Okay, and I'm using this term loosely, as the book does at this time. We've talked about batch programming earlier on. So the old idea of batch programming was where you took a bunch of programs in cardstock to the window and the lady loaded them all in, okay? So I don't mean that exactly. What I mean here is batch programs or batch processes or batch systems are those that don't require much user or any user input, okay? So the user's not sitting there waiting for it to finish. They're not trying to interact with the process, okay? These are long-running processes that don't require user input, and if you've got a computer that works like that, then maybe non-preemptive scheduling is the way that you want to go, okay? All right, so the other type is preemptive scheduling. And it probably doesn't surprise you to know that preemptive scheduling is a kind of scheduling that can interrupt the running process. So everything that we've said about non-preemptive scheduling, sort of the opposite is true for preemptive scheduling, okay? Preemptive scheduling helps us maximize the appearance that the most number of processes are being served at the same time, okay? It also helps us when we have systems that require a lot of user input, okay? Or a lot of data reading, right? Using things that where some human is going to sit there and input data or get data back out at the human time scale, okay? Here's the thing that maybe you don't think of, but even the fastest thing you can do is way slow for a computer, okay? So if the computer is going to have to wait on you to do what you need to do to process information and put that information in, right? Then the whole time the computer is waiting, it's not doing anything else. Unless we can preempt, okay, the running process and run something in the background while your slow brain is processing on what you're going to do, okay? So in other words, you can think about it like the process is waiting on you. It's actually blocked on you. We talk about it being blocked on a resource, but it might be the resource that might be blocked on is you, like keyboard entry, okay, or some calculation or making a decision, okay? And while it's blocked on you, we can schedule another program to run on the processor, okay? The drawback is, of course, that unless we're careful, right, so without careful scheduling, we're going to waste time context switching. Okay? So we want the benefit of this, but we have to be careful because if we're just switching like madmen, okay, if we spend all of the processor's time doing context switching, then nothing useful is going to be accomplished. Okay? So this right here is the reason why there's so much research into scheduling. We're going to see a bunch of different scheduling algorithms today. Only one of them is going to be preemptive. Okay, the first couple that we look at are going to be non-preemptive, and then there are going to be a lot more preemptive type scheduling algorithms later on in this chapter. That's next week. Okay. Any questions about this so far? So specifically, if a new process, where's my thing? If a new process enters or if a resource becomes ready, or if the OS context switches, then this would be a good place to activate the preemptive scheduling. Okay? Think of it this way. If an important process is waiting on you, the user, to type in some information, okay? And it blocks waiting on that information to be entered in by you, maybe it's important that once you give that information, that program has an opportunity to replace the running program, okay? Because it was an important program, it was waiting on you, you finally got around to giving it the data it needed, now it's not waiting on anything. Does that make it any less important? Does it make sense at that stage that it should have to wait again for all the other programs to finish before it gets back to you? Maybe that makes sense from the processor's perspective and just a load on the processor, right? Making sure we use the processor as much as possible. But it doesn't make sense to you as the user, okay? And so there's a distinction that needs to be drawn between what the user expects and what appears to work best for the user, and still balancing the speed of the computer, the apparent speed of the computer, by not wasting a lot of time doing context switching. Right? All right, so I've talked in broad terms, okay, about I've talked in broad terms about what makes one process have priority over another process. Okay. But now let's talk a little bit more specifically about how priority amongst processes is established and what priority means. Okay? So priority is a numerical value that indicates the importance of the process relative to other processes. Right? So it's a number that indicates relative importance for a process as compared to all the other processes. In Linux, you can sometimes manually, or you can suggest anyway, a priority when you start a process. You can give it a priority number. My recollection is, and this is a hazy recollection, but my recollection is in Linux, the higher the number, the lower the priority, okay? So like priority 1 would be the highest priority, okay? Don't quote me on that. Look it up if you need to know for sure. But that's my recollection. Okay. Why would you want to have a priority? Why would you want to give a low priority to a process? Yeah.
It's not important, you don't want to interrupt any more important stuff.
Sure. If it's not time sensitive enough, okay, that you need it to run right now, right? You can wait on it, right? So you can wait on it until maybe the system, okay, at midnight is doing not much else, okay, or 3 in the morning. The system will eventually get around to running your process, okay? And so you don't need that to interrupt and make your computer, make your system look slower than it actually is, okay? So that's a good reason to give a low priority to a process. Now, not every process is going to be friendly like that, though. Okay, not every process is going to be okay taking on a really low priority and just being run, whenever. Okay. Most of the time, processes have the idea or are built with the idea that they are going to get the processor, right, And we made a big deal before about how processes are agnostic to the fact that they are running on a system with other processes, okay? And so very few people write a program with such a low priority that it expects to run a very long time before it ever actually completes. And they're competing for the limited resources on the system, chief amongst them, the processor itself. So the scheduler has to have some kind of way of establishing priority between these processes, okay? There are two general methods, okay? Constant priority, and dynamic priority, okay? Some systems set a priority for a given process control block, usually when the process control block begins, okay? The opposite effect is to maintain a sort of running priority, constantly changing priority for every process control block. So what do you think are the drawbacks for constant priority? What would you want to be true? What would you need to know in order to assign a fixed priority to a process control block if you were designing an operating system? Yeah.
Is this giving this one process a higher priority while other processes might want to run it?
Okay, say that again.
Is giving one process a higher priority while other processes that I may also want to keep running?
Yeah, it will. Yeah. With the exception of you're generally going to pick your highest priority process. That's what your schedule is going to do. You pick in however you define priority, you're going to pick your highest priority process. Okay, that process is not guaranteed to finish running because it might block on a resource. Okay, and so it would go to the blocked state at that time. And then you would pick your second highest priority thing, okay? But if all your processes have to be given a priority value when they are created, okay, then that means that the machinations, the movement of the system through the processes can't do anything to change the relative processes, or the relative priority of the processes, okay? You can't update it. So you can imagine potentially a case where, one process arrives and it looks like a high priority process, okay? Another process arrives and it looks like a lower priority process. And a bunch of processes arrive and they're all ranked. And then all of a sudden you want to run for some reason. Maybe this process has been running for a long time, has been in the system for a long time. You want it to finish, but you can't change its relative priority, okay? And so you have to wait until all the higher priority things finish before the lower priority thing finishes. And so in effect, this is inflexible. If you're going to do this, okay, if you're going to use this technique, which is easy, it's an easy technique, but if you're going to do that, then you have to have some confidence that you can tell not only what the relative priority of any process is with all the other processes that might arrive at the time that they arrive, but also that you can tell that you're never gonna need one process to change its relative priority with another process or processes throughout their entire lives. Okay? And if you do need that, too bad you've given that up, because these are given constant priority. Okay? It's difficult to imagine a real-world system, at least a modern real-world system, where you can know all of those things for certain. So you're much more flexible, you're much better off doing some kind of dynamic priority where you maintain a running priority value for your processes. Let me just show you this table from the section. That might not be right. So if you look at table 3.1.1 from the scheduling section, you'll see a lot of different metrics that can be combined, or a lot of different parameters that can be combined to make a decision about how you're going to come to a value for priority. Okay? These are common parameters. Arrival. What time did the process arrive into the ready list? Departure. The point at which the process leaves the ready list. Okay? The time in which the CPU was attained, or went on to the running list. The total CPU time given to the process. Some external priority. That's what I was talking about, that you can do as the user. Okay, when you're on Linux, you can give it an external priority. Is there information about a deadline? Is there a priority time by which the work of the process must be completed? Okay, that's something you want to roll into your priority, because you want things on a deadline to happen first. And some other considerations like resource requirements and so forth and so on. Okay? So it looks like if you have that information, okay, you can imagine an algorithm that takes all those parameters in and gives you a value for the priority for every possible process that's running on the system. So the question then is twofold. One, you've got a design decision at hand. What of those things do you want to weight the highest? Okay, and there are different approaches as to how to calculate priority. And the other thing is sort of related to this. So what makes that value? Why is that value dynamic? Okay. Now your book does some stuff about long-term scheduling and long-term priority, and short-term scheduling and short-term priority. And as always, if I leave something off that the book is talking about, you're still responsible for that information. But I want to focus on short-term scheduling. Okay. And so what I'm going to say today refers directly to short-term scheduling, which is the more fine-grained scheduling that the operating system does, and I think ultimately more important. So the answer to this question is simple. What makes the value dynamic? Because the value is recalculated, okay, for all processes as each one well, what's the word I'm looking for? Well, I want to say processes, but as each one continues, right? So the life of a process is going to be something that looks like this. Okay? It's going to go from new to terminated. Every process is new one time. Every process is eventually terminated. Okay? And that might be because it finished, or it might be because its parent killed it. And then there's a system of cycles, okay, that looks something like this. How about ready, running, blocked? Okay. What about ready, running, ready, okay, blocked, etc., etc., etc. Any path that can be taken amongst this finite state machine, okay, always begins with ready, okay, goes to running, and eventually ends at blocked before going back to ready again. Okay? So what I'm saying is you can sometimes go from ready to running to blocked. Okay, so that's one cycle. Okay, that's one cycle in the lifetime of a process. You might go from ready to running back to ready again. Okay, because you got context switched off. Ready, running, back to ready again. That's not quite yet the cycle. Okay? Because the cycle always begins at ready and ends at blocked. Okay? So you just went from ready, running, ready. Okay? So instead of just focusing on that, we're looking at ready, running, ready. Okay, finally you're back to blocked. Okay? So it could be ready, running, ready, running, ready, running, ready, running, blocked, or just ready, terminated. Okay? Right? But once you're terminated, then it doesn't matter what your priority is. You're gone. You're not in the system anymore. Okay? Each one of these is a cycle. And if we evaluate, okay, so in order to make this dynamic, we evaluate the priority at the beginning of each cycle, here and everywhere else that we get back to ready after being blocked. So in other words, every time we make this transition from blocked to ready, with the exception of the first time when we are new, right? So when we're new, we're given a priority, and every time we go from blocked to ready, we're given a priority. Okay? Notice how these things can change, right? Our arrival time could get updated because the arrival could mean we entered the ready list, right, from being blocked. The total attained CPU time is only really the attained CPU time when short-term scheduling is only the attained CPU time for this current cycle. Okay? Total CPU time might be the overall CPU time for all of our cycles combined. Okay? But some of these values get updated, okay? Because each period of time from blocked to ready again updates those values, or resets those values. In particular, attained CPU time gets updated. Whatever real time we've had on the total CPU gets updated. So our priority can be changed throughout the lifetime of the process. Okay? Any questions about that? So just as a side note, what happens if two processes are tied with priority? Well, if they're not top priority in the ready list, it doesn't matter. But when it's somebody's turn and the two top priority processes are tied, then you have to have some kind of arbitration rule associated with the operating system. Okay, and so it could be a coin flip, although that seems somewhat unfair. So there's usually some rule in place to pick between two tied processes. Okay. So what's our main objective for all of this anyway? What's our main objective? Let's talk about some scheduling objectives. It's not on there. Okay. Scheduling objectives. Sort of the most straightforward scheduling objective is to maximize the number of processes served in a given time. Okay. And by served, I mean completed, that went from beginning to end in a unit of time. That's the objective that comes to us directly from our idea about multi-programming systems. Okay? Directly from the user's perspective about what makes a computer, quote unquote, fast. Okay? How efficient, how powerful a computer seems to be is a direct measure of maximizing the number of processes served or completed in a given time. Now, let's not confuse the issue. Processes take as long as they take. Okay? The way that you serve processes, the order you serve processes in, cannot shrink the minimum amount of computer time that all of your processes are going to take to run. Okay? Does that make sense? They take as long as they take. So if you line them up and you run them one by one, okay, they're going to take a certain amount of time. And that's the minimum amount of time that they take. And any way that you pick these blocks up and you move them around and you add it all together, they still take the same amount of time as a unit. Okay? So we're not actually trying to make the CPU faster. We're trying to make it appear faster without hurting too much the actual throughput on the actual usage time on the processor. So if we can't shrink the total amount of time that the processes take, then what does it matter in what order those processes run? The reason for that is this other metric, which we really can affect, is to minimize the wait time. Okay, minimize the wait time. So if you take any process, that process is going to take X amount of time to finish. If you start working on it and you don't stop working on it, if the processor runs it for its entire existence, it's going to take X time to finish. Okay? Since we're multi-programming, though, and we want to make it look like multiple processes are happening at the same time, we're giving up the possibility that we can always maximize that value or minimize that value, where we're only running for each process for as long as it takes to run. Okay? But we do, through scheduling, want to minimize each process's wait time. Okay? The wait time is the total amount of time that the process is in the system, but that it is not being run. Okay? So if you add together its processing time and its wait time, you get the total amount of set time from its arrival to its termination. Okay? Does that make sense? And we want to minimize that time, minimize the amount of time that it waits. And that can be defined in a couple of different ways. We can look strictly at, so I'm going to list these metrics specifically. Metrics for scheduling. We can look strictly at its turnaround time. And that's what I was talking about before. Okay. The total of CPU time and ready list plus wait list time. Since we have that idea, we can also look at, and I want to use the book's terminology exactly, average turnaround time. So the average turnaround time is what it sounds like, the average of turnaround time for all processes on the machine. Okay. Another thing to consider, though, is this idea of, quote, fairness. Okay? So perhaps at first blush, the average turnaround time by itself seems like a perfect metric for determining if the system is working well, if the scheduling system is working well. Okay? But consider a case that looks like this. Okay? I have a bunch of processes. Here they are. And the length of these boxes, okay? The length of these boxes is relative to relative to the amount of time, their total turnaround time. Okay? So we've got processes that are coming in, going out pretty quick. This one seemed to take a little bit longer. Okay? And we take this one, and it takes forever. Okay? In fact, it might be really much longer than that. But we've got thousands. We've got thousands of them that are coming and going, right? Everyone comes in, we get it done. Everyone comes in, we get it done. Small processes, perhaps, right? Each one comes in, we're done with it, okay? The total, the average turnaround time looks really good, okay? And all of these processes are happy, except for this one, okay? Because he may not ever finish. Right? Because things keep coming in and he keeps getting replaced. Right? Does that make sense? This is the idea, and it's something we want to avoid. This is the idea of starvation. Okay? When a process keeps having to wait because it keeps getting replaced by other processes over and over and over again. There's something about that long-running process. We're not letting it finish because our scheduler says, no, I don't like that process. That process is going to screw up my aggregate total wait time, right? So I'm going to put it off, and I'm going to keep on putting it off, keep on putting it off, keep on putting it off. So practically, what does that mean from the computer's and the user's standpoint? Huh? Yeah, it's not working. The computer's not working on that. That is frozen. Okay? And so if we allow that to starve, then that means we're not processing something. Okay? And this goes back to the notion of fairness then. Okay? because we want to minimize the average turnaround time, but there's still some notion that the average turnaround time doesn't capture for us. We still don't want to allow processes to starve. Okay? It's unfair. Yeah, we get a sense that it's unfair, but it's also not. Doesn't lead to good performance in the system. Not happy users. If we don't have happy users, then we're not happy. We don't have a good design. Okay? All right, so as promised, we're going to look at 3 in this section, section 3.2. 3 scheduling algorithms. And I'll just put them up on the board. All right, and there they are. So the first scheduling algorithm and the second scheduling algorithm are examples of non-preemptive scheduling algorithms. And remember what that means. That means that they are not designed in such a way that they are going to do a context switch on a non-blocked running program, a running program that is not blocked, not moved to the blocked state. First one's easy. It's first in, first out scheduling. Okay? That has a sense of being fair, right? That's how we line up for resources in the human world. Okay? You want to get a coffee? You go to your favorite coffee shop. Other people want to get coffee too. The coffee shop can't process all those people fast enough. You stand in a line, a queue, if you will. Okay? So this is by far the easiest scheduling algorithm. What's the problem with this scheduling algorithm? Okay? You always got that person who wants to write a check, right? And who is, sure. You got that person who wants to write a check and who's taken forever to make an order and finish the job, and all the other processes are waiting on that person, okay? So our metaphor is going to be strained just a little bit right now, but imagine that the president or some important dignitary walks in and wants a coffee, okay? Are you going to make the president wait? Well, if you're doing first in, first out scheduling, then you absolutely are going to make the president wait. Because first in, first out scheduling is a static priority, okay? A constant priority where all processes have the same priority. Okay, so it's like not using priority values at all. Okay, so it's the null case for using priority. Okay? So if you have, in the world of computers, if you've got a real-time system that absolutely has to be finished by a deadline, first in, first out is probably not your best choice. Okay? Because there's no way to move it to the front. It's a non-preemptive scheduling algorithm, no way to move it to the front. All right, so let's move on. How about shortest job first, or the SJF scheduling algorithm? Now there's something you need to know in order to be able to order things according to shortest job first. What's that? How long is it going to take? Is that always easy to know? No, it's not always easy to know. In fact, sometimes it's impossible to know. For complex systems, for complex programs, it's impossible to know how long it's going to take. But in those cases, even in those cases, what you can do is you can get an estimation. And the estimation algorithms can be quite complicated, right? But you get an estimation for how long something is going to take. Sort of the simplest estimation algorithm is the number of operations. But even then, even with loops and conditions and whatnot, we don't know that for sure. So we just come up with some kind of idea about how long this process is likely to take. Again, this is a non-preemptive scheduling algorithm. So the shortest job first arrives. The first job to arrive goes on to running, okay? When another process arrives, what happens? Well, remember, a new process, a process creation triggers the scheduler. So when a new process arrives, they get scheduled according to shortest job first. So if the running process has a shorter job, then it keeps running. If the newly arrived process has a shorter job, then it gets highest priority, and then it starts running. Okay? Continue. More processes arrive. That decision is made over and over again. Sometimes a process gets blocked. So we look to the ready list, we pick the shortest job thing, we move it. Okay? The good thing about shortest job first is that you absolutely will minimize your total system wait time if you are able to organize all the processes ahead of time so that the shortest jobs run and first and the longest jobs run later. Okay? That might not be obvious to see at first. This is a greedy algorithm. Okay? It might not be obvious to see at first, but consider that if you've got 12 jobs, okay? You've got 12 jobs, and they all take 1 second to run, except the last one, which takes 12 seconds to run, okay? If you run them all, right, then they take, let's say there are 11 1-second jobs, so that takes 11 seconds. The last one takes 12 seconds, okay? So the next to last job had to wait 10 seconds. The job before that had to wait 9 seconds, 8 seconds, 7 seconds, and the first job didn't have to wait at all. The last job had to wait 11 seconds and then run it 12 seconds, okay? Let's flip it. Let's put the 12-second job first, followed by 11 1-second jobs. So we run the 12-second job. How long did the first second have to wait? The first job, the second process have to wait? 12 seconds, as opposed to 1 second on our other way, doing it the opposite way. And then 13 seconds and 14 seconds and 15 seconds, okay? As opposed to 1, 2, 3, 4, right? So you can see that with that simple example, doing shortest job first, if you can guarantee that the shortest job first gets executed repeatedly, will minimize your total wait time. And that's one of the things we said we wanted to minimize. That is a simple oversimplification, though, because that presumes that you know all the jobs that are going to arrive on your system, and you don't. And it also leads to a problem that we talked about before that we said we wanted to avoid. Any idea what that is? Starvation. It's on the board, right? Starvation. A long-running process may not ever get access to the processor if it's a busy system and a bunch of smaller runtime processes keep arriving, okay? Leading to starvation. And that's a problem, okay? So both of these are sort of your common non-preemptive scheduling algorithms. All right, let's look at our first preemptive scheduling algorithm, and it is shortest job first, except it's the preemptive version. Okay? The drawback to that, so shortest job first is non-preemptive, which means that even when a shorter job arrives, it doesn't do the context switch until either the job running is finished or it goes to blocked. Okay? With shortest remaining time, right, which is just shortest job first, but done preemptively, it's not the total time that gets maximized for, it's the remaining time that gets maximized for. Okay? And the remaining time is a priority that will cause the running process to be replaced by a ready process. That's the preemptive part of this algorithm. The downside of this is it can lead to a lot of context switching. Okay? And it also doesn't fix the starvation problem. Now, overall, this is the best of those three algorithms. in the sense that it generally gives us the best, the better of the three, the smallest of the three, average total time, the average system time, total time in system. And it should not surprise you that it's because it's preemptive. Right? That's just true in general. If we can do preemptive scheduling carefully, then we can limit the amount of time in the system, the average amount of time in the system for all of our processes. Okay? And that's what we're going to pick up with in section 3 of chapter 3 next week. Got any questions for me? Okay, so I tried to give you a lot, speaking about exercise 3, I tried to give you a lot of road signs to keep you on track for exercise number 3, but there are still a lot of pitfalls that I expect you're going to have to work through, and I expect you may have questions when it comes to exercise 3. So again, don't wait to start working on that. But that's all I have for scheduling for right now. Make sure to do the reading assessment, and I will see you next week.